So apologies for the delay, but we can get going. So I have an overview here for you of what is happening in the I/O and storage space over the coming years. And it's a great opportunity here to present this and this wonderful audience, a lot of people here. And I want to take a quick tour here of what is happening in terms of hardware development, planning systems, software, and where this might be leading over the next 10 years or so. So there's not any advertisement for specific products or anything in this. It's all facts I've gathered from numerous sources. So the most important thing that is happening in the storage world is that many new tiers of storage have been developed, primarily in hardware so far. And if you look at the picture at the top here, there are several things that 10 years ago we maybe knew might be coming, but we're certainly not there. The most important one is perhaps the high bandwidth memory that is now in the CPUs. So this is given a speed bump of 10 times the speed roughly that we get to RAM. So this is an incredible improvement. On the right side, you see other storage devices. So there is a NVRAM system coming. The one on the market now is Crosspoint, which next year will sit in the DIMMs. There is Flash that is very mature now. And then there's still disk systems. So given some indication here of the bandwidths between these systems, and what is very, very notable is that the bandwidth to high bandwidth memory is on the order of a terabyte per second. If you go out over the network, we're talking about 10 to 20 gigabytes per second. So we're looking at 2 orders of magnitude difference between data movement speeds. And so the so-called hiding of latency will remain very, very important. Yeah? Similarly, Flash may have looked very, very fast, and NVRAM may have looked very, very fast only like a year ago, but with the introduction of HBM, this is actually kind of what you need now. Yeah, the main compute memory will evolve to HBM, and it will be very necessary to have very fast storage devices. These different tiers will run very different kinds of storage software. So when you look at the left side, people may be exchanging compute-ready data with pointers in it. Yeah, and perhaps the broadest view of that are PGAS systems that extend the nether space over a whole cluster. Other things might be caches, page caches between NVRAM or RAM and high bandwidth memory. When you move towards the right, at some point you'll get a namespace. Yes, something like the names of objects or the names of files. And those systems are a little bit more portable. They don't have executable data in them and pointers in them. And they're correspondingly also somewhat more difficult to construct. So we can expect that several different software layers are going to be needed if you have many tiers. Yeah? And as you will see, many systems will have many tiers. So again, the most important shift in architecture is probably the introduction of HBM, which isn't really a storage thing per se, at least not yet. Another thing that's really worth looking at for a moment is the dollars associated with storage tiers. The bottom row here is a row that many people draw up. It's the cost of capacity. And the cost of capacity goes down pretty rapidly in the direction of tape, which is like a cent per gigabyte. Yeah, and memory is on the order of 10 cents per gigabyte. Sorry, $10 per gigabyte. So it's an enormous difference of many orders of magnitude. The cost of bandwidth goes exactly in the other direction. Yeah, the cost of bandwidth to realize bandwidth with tape or disks is actually an extremely expensive proposition, and it becomes very cheap as you use memory devices. So with these competing pressures on your cost model, there are actually a lot of important system modeling questions that people should ask themselves. So, and some of these have been asked in the past, and many more will have to be asked in the future. So for example, at some point, Flash became more cheap than disk for bandwidth. Yeah, and that was the introduction of a flash cache or a buffer, burst buffer. There are different names for the same thing. The Register published that maybe around 2022, flash will become cheaper for capacity than disk. So at that point, maybe all storage might be solid state storage. Yeah, no more moving parts. But there are many other questions that one can ask. So for example, do you have the right storage to write out your memory in 6 minutes? This is a fairly typical number that HPC system designers use, that in 10% of the time you can write your memory to storage. Yeah? A more challenging question is perhaps, what is the cost of owning capacity versus using it? Yeah, the extra costs coming from managing storage systems and also from buying empty space, they might be significant in some cases. Yeah, and that, particularly with the advent of cloud opportunities, leads to some different economic models you can wonder about. So what did we see here? There will be more tiers of storage. Moving data between these tiers will be very important. Yeah, you need to bring it to the CPU to get it processed, and you will need to bring it out to take it somewhere else, for example, or keep it for a long time. I think another important lesson to pick up is be prepared for many more hardware changes. Yeah, there is a lot more in the pipeline, and I've heard, for example, that technologies like Crosspoint are fundamentally very, very powerful. And the fact that at the moment they are a little bit slower than RAM for writing, that may only be a temporary thing. And on top of that, newer technologies can be emerging. And as we've seen in the last 5 years, a whole lot can happen in a very short time. Yeah, we've seen an invasion of flash, which has wiped out the entire storage industry, more or less. And the same could perhaps happen with NVRAM during the coming years, and something new may happen. As I said earlier, comparing with the cloud would be probably a good idea, and the total cost of ownership is important. So the next thing that I'd like to look at for a while is what has storage software done to overcome performance problems? And the performance problem is here. Yeah, you copy something on a high-end Mac for which you pay a lot of money, and you get 3% of your disk bandwidth. Yeah, this is quite a recent thing maybe, and is still true. That 3% is a horrible number. Yeah, you're throwing away 97% of the bandwidth of the disk. And this can only too easily happen with storage systems. People are very aware in the HPC community that this happens for whole compute problems. Yeah, climate modeling is well known to run at roughly 1% efficiency. Yeah, maybe the SKA can run at 10%. But storage itself has similar limitations. And I want to show you what has been done about that in the last 15 years and where that may be heading right now. So going back to around 2000, the cluster or parallel file systems emerged. Yeah, and they got pretty impressive benchmark numbers, and also quite quickly showed a lot of problems for applications. I will show you a few numbers in a graph in a minute. This was followed sort of roughly in the time frame 2005, 2012 by quite sophisticated I/O libraries being built. And I'm mentioning just two. There were probably many, many more, but ADIOS and PLFS stood out by demonstrating that reorganizing the data can make a massive difference. We'll talk a little more about why that is in a minute, but they have come to the rescue of file systems. Without those, file systems would be in deep trouble. Also, in the last 10 years, we've seen the emergence of object I/O. So the cloud companies have built gigantic object storage systems. There are also many other offerings available. It has shown incredible scalability, but it lacks at the moment what you would call distributed parallelism. It's very difficult to write to an object from more than one compute system. Yeah, these objects are made for probably a single process dumping their data, and they've been quite difficult to tie in with HPC storage. That is happening at the moment. I don't know when that will complete. It remains challenging, but there are now a lot of developments to make that a reality. A newest development is to move the data into an intermediate place before using it. We'll come back to a few examples of that in new products. So if you look at this slide, there's already something standing out. There is not one storage API like the file system API. There are actually three that people probably need. There's the file system API, which is maybe called the legacy API now, or the POSIX API. Then there is an object API, which many people want to use, similar to the cloud, put and get your objects. And then there is a definite need for what you could call rich data libraries. I think that HDF5 has made the biggest name for itself. It has a very good API. And these three sets of APIs is what really will be driving storage systems. Any one of these is not going to do this. And I think that that's quite important. So let's go back to the trouble with parallel file systems. So many things have caused problems there, but you could summarize it that if you create too many files, there will be problems. Yeah, and so for example, initially millions of files in directories were problems. I think still billions of files in a directory are a big problem. Yeah? If you write too many separate bits of data into one file, yeah, so maybe lots of little bits of data that you dump in one file, you have a problem. Yeah? And what usually happens in these problems is some form of wrong alignment, where the processes start sharing low-level storage things, like they start writing to one stripe or something like that on a RAID system, or maybe a sector on a disk. And this is a very easy way to get you into a lot of trouble. And so around 2010, a beautiful paper appeared where the ADIOS library basically showed us these problems are actually quite solvable. Yeah, it's not so difficult to get this right. If you can even see it, the blue bars in the graph are the original file system performance. Pretty miserable, yeah, maybe around 3%. If you use the right I/O library with it, what you can see are massive improvements that lead to very respectable performance. And so the very encouraging thing is that the problems were resolved. Yeah, you can't really do it with the file system directly, but there is, you know, a choice of I/O libraries that will help you out. The issue is that penetrating the HPC community fast enough? Yeah, because these will be needed to overcome the problems. So what does ADIOS really do? In fact, it does relatively simple things. First of all, it has quite a different I/O API, but it's very simple and very beautiful. It's based on a group of collaborating processes. Now, that shouldn't come as a surprise, because that's exactly what HPC processes do. Yeah, it's an MPI job typically that's working together. It declares quite carefully what will be written and read, how much of it, and it will cache it very aggressively and write it out as late as possible. So it specifies this layout externally so you can manipulate it very well. And it also has lots of plugins to deal with different storage infrastructures. So it insulates the application from performance-specific features. Yeah, this is a form of portable performance for I/O, and it's, I think, very, very powerful. So one of the questions I have is, if this kind of quite beautiful and simple understanding can't become an automatic runtime optimization for every application. Yeah, why would HPC applications have to worry about this? Isn't this simple enough that, yeah, at least machine learning should be able to pick it up? Yeah, but perhaps even an algorithm can get far enough to resolve this. As I said, there are many libraries, and there are lots and lots of features. So I don't want to talk about every cell in this slide, but it's probably a good idea to say a few things about it. So one of the things is that you see here that POSIX stands out having very few features. Yeah, it basically says, yeah, you can write from non-contiguous memory and so on, but there are lots of other things you want to do. For example, collectively opening a file, opening it once for a group of processes. That's what's called a collective operation. Similarly, dealing with new attributes in files. So the history of this is a long story, which probably isn't completely finished. But one of the earlier things that happened was that MPI added a layer called MPI-IO. This layer, very confusingly, was called ADIO, the drivers. That's not the same as a DOS. There is no S in it, but it is easy to confuse. And the MPIO drivers gave a first low-level mechanism to programmers to organize their I/O better. The weather community developed a system called NetCDF. This has been under development for a very long time. I think it dates back to the mid-90s or something like that. Many versions appeared, parallel versions, new formats, and so on. But they've gradually started to resemble the HDF5 format more and more, or layer on the HDF5 format. Where IDEOS stands out is in the mechanisms and the flexibility that it's offering, and IDEOS is actually sort of becoming an underpinning for HDF5, perhaps at least intellectually. Yeah, most of the ideas, or many of the ideas, are finding its way now into that implementation. So another thing that the storage libraries will do for you is dealing with semi-structured data. So it is now very common that applications don't just write arrays of floating point numbers. Yeah, this is where the world started. Now they have a lot of metadata, which perhaps is stored in key value stores, and which sometimes requires quite complex indexing to find things. And this is fortunately becoming part of the available toolkit, but again, it's not a file system API, it's not an object API. Yeah, this is something that's only available through the I/O libraries. Yeah, the I/O libraries, I think, have become very, very important. Yeah, so I think, by the way, that HDF5 is now very widely available, but it can probably still see a lot of optimization with systems like Lustre and GPFS. I think there's a lot of work to do to make this an optimal system that helps people as easily as possible. So this is how far the I/O community got, roughly in the beginning of this decade. And new problems kept coming up. So one of the big concerns is that many small things may have to be written. And what I showed you earlier is that the different storage tiers have a fast side and a slow side. And so it is totally reasonable to expect a process to perhaps create lots of little bit of data in an NVRAM device and do that very, very fast. It is not reasonable to expect to move all these little bits of data to the next tier. At some point you'll have to aggregate this and move it as a blob. So there are many different words that describe what is needed here. Write-back caching is maybe the oldest word from operating systems courses. Containers are a very good example of doing this. So for example, containers with ZFS have a very beautiful property that you can see them as a file system and do all the small little operations. And ZFS build operations then called ZFS send to ship all the changes in a file system as one big blob to a slower tier. Yeah, and this is a very efficient way of moving lots of little things around. There are also so-called log-based file systems have been around. They write a contiguous log, very much like the stream that we just talked about coming from a container on a disk system, and they can forward these logs very efficiently. And so perhaps the best known system at the moment for that is the DDN IME system that writes these logs and can spread them over a cluster. Cray has a similar product called Data Warp, I think. So this mechanism avoids small writes. I want to go through two more problems that have become more and more current. So I want to mention, by the way, that write-back caches are not widely available yet. Yeah, you are going to be looking for them or constructing something or paying. Increasingly, the processing of data goes through workflows. So we heard a lot about, in this conference, about first perhaps preparing a lot of data and then doing machine learning to discern its properties. So what you need between these different phases is some form of coordination. The first process has finished preparing the data. The second step can get going. Yeah, with perhaps thousands of clients generating data and dozens of storage devices, you need some form of a group transaction to put these boundaries in place for a simple coordination to say, I'm ready, you can take over. So these distributed transactions are on the radar now. There have been precursors. I think perhaps the most well-known one are snapshots. Yeah, so object systems have had good snapshots, and they allow you to introduce these boundaries. APIs have been developed, and technical solutions have existed for a while, but the most beautiful system that's perhaps under development in this is called DEOS. This is a big DOE Intel HDF5 group collaboration building a next-generation object store that addresses quite a few things. So it has these beautiful transactions that allow you to have boundaries. It's also a very lightweight system that can write to extremely fast storage devices with redundancy and with forwarding. And it should be scalable to some of the biggest systems that we are thinking about at the moment. It's not ready, and it has been around for a while, so they are currently building a second pre-production version. It's all open source, and so you can easily find it on GitHub or search for Intel and DEOS. So I think what is very important to realize, though, is that this is a low-level system, not an end-user system. This needs to be used with HDF5, with a file system driver, or with an object driver. Yeah, this has to become a full solution before it will be eminently usable. But it's a very important technology to deal with new storage devices in particular. So the last mechanism that I'd like to talk about are for a collection of problems that I think might be the hardest I/O problems that I've seen. So there is a significant set of HPC problems where very many very small data packets have to be exchanged. And perhaps one of the beautiful examples of this are the so-called adaptive mesh refinements, where when the meshes are reorganized, lots of things need to be aggregated, and this can lead to a total storm in the cluster with I/O going from every place to every other place. And as you might expect, that doesn't work very well. So for these problems, again, quite good solutions are being found, and it turns out to be an issue of data staging. So instead of pulling lots of packets multiple times, they are being staged in some form of intermediary node, and then you pull them out to the destinations from the intermediary place. So this is a mechanism a little different from write-back caching. Write-back caching eliminated many writes, and file staging eliminates many reads. Staging is a form of caching also, yeah, but this is kind of the opposite direction of the traffic. It's bringing the data to you rather than writing it to a storage device. So no surprise, DEOS experimented with this very early on with a network driver, as they call it, for data spaces. There are also very beautiful custom libraries being built. One I heard about recently was from the Munich LRZ called PUM. But these systems are in their infancy, and I think, again, the mechanisms are not so complicated. Can we perhaps look forward to having this available to everyone without a lot of head scratching? Yeah, could it even be detected that this should be instantiated dynamically when an application performs this kind of I/O. It's easy to detect, but it may be difficult to react to it. So the last mechanism I want to mention is that with the tiers and the enormous price differences between tiers, the movement of whole files is becoming more important too. Yeah, so previously this did happen with archive systems based on tapes, but those tapes are probably becoming too slow to deal with flash-type performance for the intermediate tiers. So Los Alamos has built a rather beautiful system called campaign storage for this, and they have a little file system driver for it. And the purpose of campaign storage is purely to bring data between a larger, cheaper tier of storage and a fast tier. So the system design already came up with some economic constraint. They said, we want very fast storage, but we can't afford too much of it. So we're also building a very big data lake, some people have called it here, yeah. The Maravs is actually a sea, yeah, so it's all kind of data in the water. And the problem is moving things back and forth in parallel. So obviously in the HPC community, parallel movement would be very important. The cloud community has developed similar systems, and there are some very beautiful ones called IPFS and Upspin. I think both come out of the Bay Area. One has a initial coin offering story attached to it, and it is now a very rich startup suddenly. I think that's IPFS. And those systems, I think, have some advantages over the lab systems, but they are not parallel. Yeah, but they have higher data integrity and perhaps more beautiful management. So the campaign storage is a new tier of what you could call perhaps cheap disk storage. Yeah? And it will have intermediate bandwidths, much slower than parallel file systems, but much faster than an archive. Perhaps the pricing will at some point become competitive with archives and it can replace them. Yeah, I don't think that's quite there yet, but that may happen. So that may sound like a lot of I/O mechanisms, so I thought let me put them on one slide because it's actually not so many. Yeah, so we talked about layouts and buffering, transactions, write-back caching, and partial and whole file staging. Yeah, so it's actually not a very long list. And not all of these are easily available to end users, yeah, but they are on the radar now as the key constructions. So I want to move now to show you a little bit about I/O systems that are being planned for what you could call notable upcoming systems. Some of these so I'm sure that the details are not exactly correct because these things change into contract negotiations, and in other cases one feels always a little bit out of date. But let's look a little bit of what's happened up to now and what is happening right now. So what we've seen so far is that people would buy racks with compute nodes, and then there would also be disk enclosures with servers. Yeah, and the disk enclosures with servers are the I/O storage systems. And people have achieved a lot with this, you know, a terabyte per second. Typically, the size of these storage systems is on the order of 100 times the RAM in the system. Yeah, Lustre and GPFS have probably emerged as the winners for large systems. For smaller systems, many, many different file systems are used for this. So in the last few years, people have added flash caches to this. So the flash caches are maybe more like 10 times RAM, so they're significantly smaller because they're much more expensive for capacity, but they are cheaper for bandwidth. Yeah, remember the economic pressures are different. Yeah, and so people elected to have smaller amount of this very fast storage. So some people run file systems on these flash systems, others run the DDM IME systems or the Cray data warp systems. And this is what you could call the first emergence of the burst buffers. Yeah? And this is a good example of tiers entering the systems. So if we look forward, Here are three interesting systems that are currently, for some there are RFPs, maybe for others there are almost contracts and so on, and some, the SKA system is, I think, just in the design phase. So let's look at the 2020 system. So that system is perhaps planning to use many ZFS Lustre or GPFS servers, so running on flash but keeping the file system model. The I/O that people want to see is maybe 5 to 10 terabytes per second. Yeah, the memory in the system is 2 to 5 petabytes, and so there's maybe 100 petabytes flash. Yeah, so this is the normal proportion. And so these proportions, again, they are, you want, in the first tier of storage, you want definitely considerably more than your memory so that you can dump the jobs into the fastest tier of storage. You also want to do that relatively quickly. You don't want to have to wait an hour to write to the fast tier of storage. You want to do that maybe in 5 minutes or so. 10% of the time is what maybe people say, roughly. And so these numbers, they should roughly work out to that. So there may or may not be a burst buffer, but there will perhaps be a secondary tier of campaign storage in this system. Yeah, and so the campaign storage would be much larger, and it would be used to move jobs in for a somewhat longer time. Yeah, like maybe a week or a month or so. I thought I'd include a little outlook on what the SKA system would have. So there will be two of these systems, one in South Africa and one in Australia. So they're a little bit different from some common HPC systems. They are very, very read intensive. So SKA expects to need to read 10 terabytes per second sustained. That's a pretty high number, yeah, but it's not out of reach, I think, for 2025. And the write for the ingest of the data is the highest I/O number, and it's on the order of a terabyte per second. It's, by the way, a little bit different for the two telescopes and so on, but this is probably roughly right. There is an output archive, yeah, it could also be a slow tier of storage, roughly of an exabyte, and it's that's half a petabyte per day for 5 years. Yeah, so that's roughly what an experiment produces in day. So it's interesting that an exabyte goes in from the antennas, a petabyte comes out. Yeah, so that's what the SKA machine does. It's a big data reduction. The real challenge for SKA is perhaps not the I/O, but the memory bandwidth. Yeah, they are looking at 200 petabytes per second in memory bandwidth. That will be quite difficult to avoid that requirement. That's memory bandwidth after cache reuse. So that's honest memory bandwidth that needs to be delivered. So a system that is, in time scale in the middle is the much talked about exascale system for the US. There are actually two in that RFP, I think. One is for 2021 and one for 2022. They're looking at having 10 petabytes of RAM, and you can immediately start doing the math again. Yeah, so you want 100 times that in storage, and you want to write half of that in 3 minutes or all of it in 6 minutes. So you're looking here at 30 terabytes per second in I/O. So that is a significant step up from where we are now. Yeah, maybe at the moment, people in the biggest systems have perhaps on the order of 5 to 10 terabytes at most to their burst buffers. Yeah, and bringing that to 30 will not be so easy. The 2023 machine 2022 machine explicitly specifies to have a capacity tier and a performance tier. Yeah, so they're bringing the tiers even into the specification. And the total storage will be half an exabyte. They are proposing a POSIX model. Yeah, although I'm sure they need the libraries and the object interfaces that we've talked about. They are going to leverage a namespace. And frankly, I think that their namespace requirements are not so difficult to meet. Yeah, I think they could almost be met today with like 1 million stats per day or so. That's quite doable. So this is what people are thinking about for future systems. Let's also look for a minute at what software might be emerging. And there should be almost no surprises anymore in what I'm putting down here, because we've seen why it's being developed. So the application needs an I/O stack, I think it's fairly firmly decided that the I/O layers below it will have two layers. Yeah, there will be an I/O library with next to it an object interface and a file system interface. So these interfaces will be available to the application. This will use some kind of storage layer below it, and that storage layer is more open for discussion. We'll come to that in a minute. What are the options here? Below the storage layer will either be the OS or the OS not, yeah, meaning bypassing it. It's very attractive sometimes to not send things in the kernel. It's also, by the way, sometimes very attractive to use the kernel. So let's look at what these storage layers might be. There are many, many candidates. So I think that to some degree the incumbents are going to be the most likely candidates, at least for a little while. And so that would be evolving file system technology. Yeah, particularly because the big machines are relatively nearby in time. It will be likely that perhaps they use file systems to store stuff in. The new DAO system was created and designed for these systems, so it's definitely a candidate. I also think it's extremely beautiful system. It has objects that can store metadata or file extents. There are also quite a lot of emerging research projects. Yeah, many people here in all around the world are experimenting with using Ceph with some form of metadata to store HPC data. You know, Ceph has made incredible inroads, and it's a very beautiful system. So it's not surprising people would want to use that. It has, for example, support for tiers, migration. It has a very sophisticated layout of data. There are also other projects. So there is a big research project in Europe. The ADIOS teams want to move further. And so one of these could become a candidate, just like a new or an existing corporate product could poke through here. So as you might imagine, I've thought a lot about the business side of these I/O systems over the years. And I think I want to leave one important message here. So if you build a new I/O system, it's actually ultimately a pretty expensive business. Yeah, so maybe you can bring it onto a top one system for not so much money, but to start to support it very widely and make it more usable and deal with a lot of use cases will require, you know, a solid team and a solid stream of cash to do the work. If there are too many offerings of new systems, the funding might get very diluted, and as a result, the incumbent might actually become the strongest candidate. Yeah, it's probably necessary if people want a new system at some point to focus on one and say, that's the one that we're really going to go after and now push it. Yeah, and maybe you do it with 2, but you probably don't do it with 10 different systems, because at that point, there just isn't the money to go around. So let me wrap up with a few thoughts. So first of all, I have some questions, technical suggestions that I want to mention. Many people have always talked to me about, we really want to use local storage. Every node has a disk, every node has a flash device. If you look at those devices, they're amazing. Yeah, they sit on one node and they typically score perhaps, you know, 20, 30% of your parallel file system performance just out of one node. Maybe that's not completely true for I/O, but for metadata that may be more than true. Yeah? I think a new storage system should be able to leverage them all. Yeah, and to take that benefit when it is available. But those systems have not seen much development yet, and I think they're difficult to construct. Yeah, you will have a lot going on if every node has a storage subsystem and you need some coherence, but it's probably quite important. Another thing that seems to be a little bit neglected is direct I/O to accelerators. Yeah, particularly GPU memory. At the moment, you have to drag that through the CPU memory and then send it to the GPU. That seems like a waste of moving data. And moving data is an expensive business. Yeah, there are numbers for that. So I think that this needs more attention. I already mentioned some form of maybe machine learning or a good algorithm to handle layouts and scheduling. Another very important thing where storage has fallen behind the databases very, very badly is in a declarative approach. People need, new kinds of data organization, and so objects are examples of that. All these tables in HDF5 files are example of that. And I was very interested to hear that UCSC has an effort to define a declaratively defined storage system, a little bit like the SQL schemas for databases. Yeah, they've been unbelievably successful for the last, 30, 40 years. Yeah, and some of that could be used. Another thing that we are not getting quickly enough, I think, is non-volatile transactional memory. So transactional memory is an extremely beautiful programming system that eliminates locks. You can basically say, do a computation in memory, and either all of it goes through, or it will roll the state back. So you don't have to lock all the individual steps. You get a natural competition between transactions, and most of the time, one of them will succeed. To do that for non-volatile memory is considerably more difficult, but it would eliminate the same big mess of locking and waiting that is beginning to enter even the newest storage systems. Yeah, I think it's quite regretful that it's 2017 and we are locking little extent ranges to avoid concurrent writes and so on. That's not such a good situation. So here are some other challenges. By far the biggest challenge facing I/O for HPC is to agree on APIs. Yeah, so I'm absolutely horrified that many new proposals come with a new API. There is no object API after 15 years. Yeah, S3 is common, but there are 10 or 20 others that all have some advantages. None of them are very usable for HPC. Yeah, so can this community come to an agreement that a good form of POSIX object and perhaps HDF5 or so is an API that we can all use and all expect to be there? And perhaps a cloud player like Azure could play a big role here in making something like this the standard offering and pushing people a little bit to expect that from what is provided to them. So another big challenge is get rid of these parallel file systems. Yeah, I mean they're becoming old, almost 20 years, and they seem to be very difficult to displace at the moment. Yeah, and perhaps the complexity of I/O systems is very high, but we would hope to have alternatives. Yeah, at least for a matter of choice. So I think the conclusions are quite optimistic. There are beautiful, simple systems coming around at the moment. Yeah, there's a lot of understanding in dealing with performance. The hardware expectations have, I think, taken everybody by surprise. Yeah, who would have expected that Flash would become like a commodity storage device? Yeah, that we would see gigabytes of performance per second in a laptop. Yeah? So for 2020s. Yeah, not for 2022, but I think we should set our eyes on, above all, a new system that we can all love. Yeah, there is an enormous amount of hate for storage systems, and I know exactly why. And I hope we can find something that people will find much more pleasant to use and has many, many less difficult corners. I also think we're going to see a petabyte of I/O per second, and a billion file namespace operations in a second in production in the 2020s. Yeah? Thank you very much.